Hello everyone, welcome to a Pragmatic Guide to Games Code Optimization. I'm Gavin Freyberg, I'm a Director of Engineering at WB Games. Spent about 20 years engineering, and for the last 12 years I worked on 60 Hz fighting game, Injustice, Mortal Kombat, NetherRealm Studios games. It's worth noting fighting games have really hard frame targets. You can't afford to slip past your performance deadline or the feel of the game changes incredibly. Dirty secret, this slide is to reassure me, not to reassure you. Okay, so what is code optimization? My definition is it's refactoring or reworking code to decrease resource use. Now, the Oxford Dictionary has a specific definition for optimization, but we don't care about that one. So ultimately, why we optimize is to free up resources to do cool things. You may be optimizing to get onto a lower spec piece of target hardware, but in reality, you just want to do all of the cool things you're already doing on that piece of target hardware. So when it comes to optimization, coders have a dilemma. As you go through the development cycle, the knowledge that you have increases and you know what to optimize and how to optimize it a lot better. But as you go through the development cycle, your ability to make changes, both in terms of time and in terms of your use cases hardening and expectations hardening, gets a lot worse as well. So there's kind of a balance in when we optimize. So when should you optimize? Well, my view is continuously as part of your normal development cycle. If you're leaving optimization right to the end of your project, then you're going to have poor performance as a general rule, and that impacts gameplay, it impacts, it creates broken windows where people just check in stuff and that performs poorly because they don't know any better, because you're already outside of your performance bounds, and you end up with people becoming dependent on this bad behavior that's unsustainable in the long term. But premature optimization can hurt too, and I'm going to talk about that later on when I talk about some trade-offs and concerns that come up with performance optimization. So, optimization flow. A lot of people have probably done this, but this is how I would define the optimization flow. First thing you need to do is you define your goal. What are you trying to achieve? How much time do you want to get back? That type of thing. Then you have to measure. I'm going to talk about all of these steps in the following slides, by the way. Then you need to identify and perform your optimization, and then you need to measure again. If you do not measure your optimization, you're more likely than not to not achieve what you're targeting. At that point, you've got a decision. Do you keep it or do you not keep it? And it's not as simple a decision as I wrote my code so I keep it. And then even if you're keeping it, you might have to go back to the beginning and perform more optimizations. This is an iterative cycle. It is not a once-off. You don't do all of your optimization in one pass. And then finally, you might be done. Okay, so going through those sections, first defining your goal. Are you targeting a certain system of your code? Is there a specific thing that you want to get faster, or maybe you're just spending 2 weeks optimizing? What's your test scenario? Really, you need your test scenarios to be reproducible. Sometimes that means you get determinism in your code. I love deterministic code bases. If you can manage it, it's great. Do you need to write scripts in order to reproduce your scenario? Often, it is better to write some automation to recreate your scenario and be able to retest right through the game with those performance metrics and keep track of it than it is to once-off this stuff. And then there's the general stuff of what's your budget? Can you afford to spend more memory? What CPU time budget do you have? Can you take on additional latency with the work that you've got? And are there quality trade-offs you can make for your optimization? Measurement. You don't know anything until you measure. If you're going into optimization without measuring, you're guessing, and you're probably not going to make the right guess. So, first thing, you need to measure representative use cases. You need to use realistic data counts. You need to use similar build settings to your release build. I don't say the same, it's almost never the same build, but you need to use similar settings. And you need to be on the hardware that you're targeting. If you're trying to optimize on a platform that is not the hardware that you're aiming for, it's likely not going to do you any good. So another important thing from measurement is you need to be able to attribute the cost. You need to be able to work out exactly where your time is going and what is causing your performance problems. But like anything in this world, these things don't come for free, and there's a performance cost in and of itself to your measurements. So you've got a trade-off, and generally you want to be able to switch on and off pieces of your measurement. Finally, averages can be really deceiving. When we measure with averages, we end up missing spikes and other critical pieces of information. So you often need more than just the averages. Basic starting point for code optimization is to throw in some manual instrumentation, CPU timers, accumulators. Unreal has the stats system. Unity has its own methods as well. What you're looking for in some manual instrumentation is for it to be minimally intrusive, to have even overhead so that you're not creating weird data, and for it to be consistent over multiple runs so that when you come back and measure the second time, you aren't getting performance deltas coming from your measurement system. You can also measure your instrumentation lib. If you're using CPU timers, for instance, throw them in a million times in a tight loop, time how long it takes to run that loop, and now you've got a good idea of what your overhead is. That means you can predict, if I have heavily instrumented this piece of code, what would I expect to happen in terms of negative performance impact? Also, you want to be able to compile this stuff out, just in general. Profiling tools. So profiling tools are pretty critical to this area. Like, you can write your own stuff, but you really want profiling tools. There are two major modes of a profiling tool. One is instrumented profiling, where you're putting in markers yourself, or you're instructing the profiler to mark certain segments of the code. They're great. You get call counts and generally more timing information by using an instrumented profiler. But unfortunately, they tend to be very performance detrimental. So you've really got a trade-off there. A great all-round tool is sampling profiling. Almost every profiling tool I know of allows for sampling profiling. Certainly the hardware-supported ones do. I often use this for first discovery, trying to work out where I should be looking with my instrumentation to begin with. And sometimes you can do the whole profiling job with it. They're really bad for measuring overall impact because they use percentages. It gets really, really hairy, especially if you change a couple of things to actually tell what got better and what got worse. So I've got a demo later on where you can see some of that. Okay, catching spikes is a really useful thing to be able to do, and it's really hard without a good profiling tool. Again, you can write this stuff yourself, but it gets really complicated really fast, and the more information you need, the worse that the complications get. But especially for spikes, visualization really, really helps. It's very hard to understand what's going on with spikes without some visualization. So I've just listed a couple of example tools there. I'm not listing the ones that are on platforms like Sony, but some of the dedicated platform tools are really, really good and are in fact my go-to tools. Here's a note on the critical path. When you are using profiling tools and you are running async or a lot of async code, you end up with graphs that maybe look something like that, where you've got, we've got what, 5 tasks there, 6 tasks there, and if you look at it, task E is taking the most time. But when all's said and done, optimizing task E or task D or task B is going to get you very little time back. You actually need to understand what your critical path through the system is in order to make the correctly targeted optimization if you're just looking to get frame time back. If you're running an instrumented profile and naively on that, you'll see task E coming up as your highest CPU use, and you're not going to get a millisecond of frame time back or any frame time back by optimizing it. There is a caveat. When you have a lot of heavy data use on another thread, because of the way our hardware works, it will have a performance impact on the code that's running on your critical path, even if it's running on a different thread. This comes from cache pollution. It could be that you've got a second hardware thread running on the same core that's running your critical path code. So you can't ignore it, but it's certainly not what you want to target in preference to everything else. Quick note on frames per second versus milliseconds. This is one of my favorite things to hate. If you have, like every team in the world, have a frames per second counter up on your screen, and that's how all of your staff are measuring whether the performance is bad or not, you're actually doing yourself a disservice. Because when you hit half your frame rate, you're actually 100% out in terms of your frame time. You have to get 100% of your target frame time back in order to get half of your frames per second back. So my recommendation is get used to using milliseconds and don't use frames per second as a measurement of what your performance is like. Okay, on to ranking optimizations. So optimization requires understanding. It's as simple as that. You can't optimize your code without getting a good understanding of it. You can do spot optimizations where you target a very narrow scope without understanding the entire thing, but you still need to understand what's going on in that small piece of code that you're optimizing. And you need to know more than just what the lines of code say in most cases. You need to understand what the data's doing as well. So when it comes to actually ranking the optimizations, you need to be aware of what code scope you've got, what your expected gain is, how much hardening you're prepared to take around your use cases, the behavior change that you're prepared to accept, memory or other resource impact, and impact to maintainability. And I'm actually going to go through those one at a time. So, code scope. This is the way I choose to define it. It's certainly not what everyone would use, but this is how I think about it in my head. At the very left end, you have a spot optimization. Spot optimization is really narrow. It's probably going to be within or almost by definition, it's going to be within a single function. It's going to have low risk and low knock-on effects, or likely low knock-on effects. As you move to the right, you get into in-module optimization. Now, by module here, I mean anything that has a relatively well-defined API boundary. So you're in a piece of code that's self-contained, that's relatively encapsulated. You're not dealing with everyone coming in and accessing the data and mucking around with it. You're going to touch a bunch of functions. You're probably going to be changing the data formats, maybe the data flow through that module, but you're not really impacting the systems outside of that. Final mode you can be in is cross-module optimization. You really don't want to be here. Cross-module optimization is pretty much hell for someone doing optimization. It's just bad. You create loads of risk. If you can stay out of that mode, you want to be out of that mode. So, a couple of quick notes. Obviously, modular code gives you flexibility when it comes to optimization. Yeah, go figure. It's good software engineering practice, right? If you write modular code, you have more flexibility to change that code. It's worth noting that it's not just when you're writing it, it's when you have to come back and get it to run faster too. Also, the code scope is not equal to the impact of the optimization. You can have a one-line optimization that improves the performance of your code drastically and by reducing the big O. So, in fact, we have one of those in the demo later. You can also introduce or remove resource contention with a spot optimization. So the code scope is not the impact. So optimization concerns, more optimization concerns. What is your expected gain? Your best case is that the thing becomes free. It doesn't happen very often. Worst case is the performance gets worse. Definitely tends more to the worst case than to the best case. Reality is generally somewhere in between, but often if you're trying to work out what the expected gain is before you start on the optimization, you might have to put in some specific measurements, you might have to run some test cases, just to try and get some idea of what the actual time you're going to get back is. But as a general rule, you end up having to perform the optimization and measuring it before you actually know what it's going to be. Hence why you iterate. Hardening around use cases is an interesting topic. As you go through development, you will end up hardening around your use cases. People will expect the behavior that you have in your systems and expect everything from how long they take to what threads they run on. It just happens. It's the nature of expectation setting is that as you go through the project, these things will harden. So another part of hardening your optimizations, another thing that can harden expectations is adding certain optimizations to your code. There are a whole heap of optimizations that you can do that are actually hardening around certain use cases. A great example is if you put in something like a quad tree or an octatree into your code. Your expectation there is that not everything in the world is moving or that queries against that quad tree are going to be small. They're not going to take up the scope of the entire quad tree or octatree. If everything moves and you have large queries that cover the entire quad tree or octree, it's not going to be an optimization anymore. It's just going to be a performance drain. So even something that we treat as pretty routine, like that's hardening your use cases and introducing design decisions into your system. All right. So behavior change, is it okay? Like, the honest truth is only you and your artists and your designers can tell at any given time. Please don't discard behavior change as an option, but the later you get in the project, the more likely it is that behavior change is not going to be okay. Code maintainability is a huge concern when it comes to optimization. Again, we'll go back to the quad tree example really quick. Putting in a quad tree makes your code a lot more complicated. There is a lot more going on there. If you can just do a simple loop to do the scans that your quad tree were doing, the code will be a lot shorter and a lot easier to understand. That's the nature of the beast for most optimizations. You actually increase your code and often obfuscate what your purpose is in order to put that in. Finally, when you are making optimizations, quite often there's a memory versus time trade-off. You might be adding caching to the data that you're accessing in order to make it faster and not recalculate stuff. That's got a memory cost, and the size of that memory cost is going to be dependent on how aggressive you are with caching and how much information is there. So I've got some sort of guiding questions that I like to ask when I'm engaging on optimizing a certain piece of code. Every single one of these optimizations, as I said, has their own trade-offs. I'm not going to go into high detail on them. I simply don't have time. So first thing is, like, are there specific hotspots? Generally, if you can find some low-hanging fruit and do something like removing ordering in an array that shouldn't have been ordered in the first place, or remove that unnecessary copy of an array, that's going to get you a lot of time back really cheap. And it's surprising how often those types of things come up as real optimizations that save you a ton of time. So first thing is do anything quick. Another thing is there costly math? I see this all the time from all sorts of code. There are a bunch of math functions that we call just routinely that are actually really expensive on the hardware or in software. Square root, power, sine, cos, tan, all of those functions, they're expensive. If you can reduce or eliminate the use of those functions, you'll get a lot of time back. Also with math, it is amazing how often, if you just go and write out the formula like you were in college and go and try and simplify it, you will find that you get a bunch of time back. I've got one specific example where I optimized some mirroring code way back in the day. It was composing out the skeleton, then doing the mirroring operation, then decomposing the skeleton in order to do the mirroring operation. I wrote it out. It turns out that the matrix math could have everything eliminated that caused the compose. So this code turned from being something that was an absolute performance dog to something we could call all the time, which changed the behavior of the game from that point forward. Okay, is there a lot of time in object construction and deconstruction? Well, classic example, pull them. Are you cache missing a lot? Cache missing a lot often looks like showing up high, if your profiler doesn't specifically show cache misses, as like a high amount of time on the first lines of code within a data loop where you're processing a large data array. Lots of things you can do there. You can remove a bunch of data. You can actually reduce the size of the types. And there's array of structures to structure of arrays conversions, which are kind of undersold these days, I think. If you've got huge arrays of data to process, you can introduce some data parallelism. Go wide on multiple threads to solve that one. If you're not using all of the data that you calculate, it's amazing how often we will calculate 5 things at once, and actually in half of our use cases, we only need 1 of those 5 things. So determine your requirements and separate the calculations out so that you're not doing that. Are you calculating the same data repeatedly? Again, a classic one. You're query some function 10 times in a frame, and actually that function's really expensive to call. And instead of caching the data and marking out the edges, you're just doing the calculation every time. Well, you can get a massive amount of time back by caching the data. Does this work even need to happen now? So there are 2 cases here. Like frequently you can just move it around and stick it on another thread so that into what becomes a term called Ivan free from my studio, which is it becomes free because that was dead time anyway on the frame. So you can just shift it into that time and suddenly it's got no cost or no impact to the critical path is a better way of putting it. Also, if it doesn't need to happen on this frame, you can often frame span the work and even conditionally execute the work in order to reduce spikes on the frames that you're interested in. Okay, are you spending most of your time outside of key code? This could be like you have a big loop, and in that loop you have a specific piece of code that you're running to do something clever, but that code's taking like 1% of the time and the loop's taking 20% of the time. Well, you might want to partition your data in that case, separate it into an active and an inactive list so that you're only processing the elements that are actually important. That one's got some trade-offs, which I'll talk about later. Are you taking full advantage of your hardware? Like modern processors have some pretty blindingly fast vector units. If you're not taking advantage of them and you're doing heavy math, you're leaving a lot of performance on the table. You can also move work to other threads if you're not using all of your hardware threads. You can also break up your work if you are using multiple threads into smaller work so that it can slide into time slices outside of your critical path. So if all else fails and you need time back, my rule of thumb is go and refactor it to turn it into more modular code. So go and take your crazy code that you're having trouble understanding and can't work out where an optimization is, refactor it in order to get it into a more understandable state. This is a knowledge gaining exercise. It's not an optimization. It's a good chance it's going to cost you time. But as the next step, you can go back in and optimize that code and see how far you get. Okay, keeping optimizations. Look, don't be afraid to discard your change. The number of times I and other people I've worked with have spent weeks on an optimization, only to come back and say, yeah, you know, it didn't get me a lot of time back, like tiny, tiny piece of time back. And it's like, no, that's not worth the code complexity. Get rid of it. When you're engaged in optimization, you have to be prepared to throw it away. I know it's your baby. I know you wrote that code and you feel for it, but throw it away. It's not worth it if the trade-offs aren't there. Okay, so back to the flow. We've talked about defining your goal. We've talked about measurement. You do that twice. Well, at least twice. You identify and perform your optimizations. You make a decision on whether you keep it or not based on all the things we talked about, and probably a whole heap of other things. And then, and only then, if you've reached your goal, you can say, yep, I'm done. Okay, I'm going to go through a couple of notes, and then I'm going to dive into the optimization demo, which I'm probably going to have to go through pretty quick, for which I apologize. So memory access is really, really expensive. If you don't understand that yet, you should take note of it, because it's a huge part of performance. Like, the CPUs are pretty blazingly fast at just doing straight math in the logic units. Memory access is the slow bit. Mechanical sympathy. If you are targeting one platform and you are able to optimize your code around that one platform, you will likely have a better game or a more performant game than if you were targeting multiple platforms. It's just kind of the reality of the situation. You can sort of go and look at like the platform exclusives to get an idea of this. They tend to be more impressive games than the non-platform exclusives. Multi-threading, it's really too big a topic for me to get into. I love multi-threading. I'd talk about it ad nauseum given a chance, but the thing that it's important to remember here is that it's not free. You don't just get to take your work and split it out evenly over X many threads and get X time improvement. You have to pay for the synchronization frequently. You have to consolidate data structures after doing the work. It's not free. But it can be a super easy optimization to make in the right circumstances. So you should at least be aware of what the trade-offs are there. Partitioning data, this is what I was talking about earlier. It's incredibly use case dependent. Now, this could be quad trees, oct trees, active and inactive lists, all of those types of things. Anything where you're partitioning your data and changing the behavior around that data, you're hardening use cases, and you should understand that. You should make sure that before you partition your data up, that you really go and get a good understanding from your designers, your artists, about how they are intending to use the system in the future, and make sure you really well understand the use cases you have today. Targeting worst case performance. I love to target worst case performance. It's a rule that I lived by for a long time. Get rid of spikes, target the worst case, turn it into more of an average case. You get way more frame stability, which means you can actually use all of the time on the frame rather than having to leave a large period of time as a buffer at the end of the frame. And in general, you get the best use of your resources like that. Okay, don't prematurely optimize, but don't be naive either. Like, do some ballpark pen and paper math. If you're just writing your code and checking it in, and you haven't even bothered to work out what your expected use case is and done some math on what that's going to look like, you're probably making a mistake. For instance, if you have 10 items, you don't care if it's an n-cubed algorithm. If you have 100,000 items, you care pretty deeply if it's an n-cubed algorithm. So you need to understand your use cases and ballpark it a little bit. Okay, here's my demo. It's crap code. It's code that I wrote being deliberately naive and specifically for this talk. So don't expect magic code. It's not great. It is relatively clean. What it is a 2D particle system. There's a fixed particle count per simulation, and that particle count is maintained on every frame. So if particles die, they respawn on the next frame, or so that you've always got that particle count. Simulations last for 10 seconds. The simulations are run with up to 100,000 particles. The particles are randomly positioned within a 2,000 unit area. They have a lifetime of between 0.5 and 1.5 seconds. They've got no velocity when they're spawned, and there's a small moving circle that accelerates the particles, and they decelerate again after they are outside of that circle. So it uses CPU timers for aggregates that are just based on standard chrono. I used MSVC CPU recording for analysis, and that's a sampling profiler. I only profiled the 100,000 particle case, so when you see the profiles, that's on the 100,000 particle case, which is what I'm targeting. The aim, or my goal here, is to simulate 100,000 particles 1,000 times per second, so less than 1 millisecond per tick. Okay, so into the code. That's all of the constants, basically, for the particle simulation. I hope you can read it. I tried to make it as large as I could on the slide. The tick itself is, first we spawn particles, then we update the particles, then we remove the expired particles. Spawning new particles is as simple as newing up a particle, throwing it into a vector of unique pointers to particles. They have a start time, a random end time between that 5 and 1.5 seconds, randomly positioned, and no velocity. So push it back onto the array. Removing the expired particles, just iterate through all of the particles, find out if they're past the end time, and erase them from the array. If we erase one, we don't increment the iterator because it's no longer there, and we don't want to skip an element. Updating particles. You can ignore the little bit at the top. It's just calculating the position of the circle that pulls the particles to it. We go through all of the particles. We work out how far we are from the center of that pull location. We compare it to the radius of that circle, and then do some acceleration math to pull it towards the center of the circle. If we're not doing the acceleration math, we do the deceleration math, which is using POW to apply a damping factor over the time period. So the reason why it's using POW is because that allows, it no longer matters how long the frame is, sort of, and we get relatively consistent dampening. Okay, so here's the first measurement. You'll see the little grid, the table on the right. It gives the number of ticks, time, average ticks per second, average the number of milliseconds on average, and the max tick time. When you see the orange highlight, that means new results. When you don't see the orange highlight, it means it's the old results, so you can compare. As you can see, it is distinctly non-linear. It's only getting 90 frames out of a 13 millisecond run. That's interesting. It's meant to stop at 10 seconds, not 13 seconds. Well, it turns out when you've got a 4-second maximum tick time, that's probably not so good. Okay, so we do an analysis, performance capture. And we find that 93% of our time is on this one line, which is erasing the particle from the array. Okay, so what's going on? Erase is order preserving. If you erase something from the middle of an array, it's going to shuffle everything after that in the array back. And in fact, in this case, you tend to have the older particles at the beginning of the array, so it's basically your worst case scenario. We do this a lot of times. It turns what should have been a linear operation into an n-squared operation. Here's my example. We're going to change this code. So do we need to retain the ordering? No, we absolutely do not. So we're going to swap the last element into the position of the current particle that is past its expiry date, and then to remove it from the end instead. So the consequences right now, memory's not released from the array anymore when I make this change, but I consider this a spot optimization. Now, this may look like, oh, yeah, that's a really easy optimization, and it is. Do you know how many times I've made this optimization to code and had results something like this? Oh, sorry, there's the code change. Results like this. Okay, we went from 90 ticks over 13 seconds or 14 seconds to 1,352. It's like a 19 times performance improvement or something like that. It's pretty whack. And we've now got a relatively linear timeline. That was one change. And again, that optimization is one I've made many, many times in production code. This is not an unusual thing to do. Okay, so now we've measured again. We're going to make another analysis. Where's the time going now? Well, most of the time is going on applying the velocity, that line where we're decelerating. Okay, so what's going on? Oh, actually, I should point out. One of the things you may notice is that the hotspot is actually an external code. It's not an internal code. Now, that's a hint as to what's going on. It's actually that power is expensive. So we've got 48% of CPU going on there. Power is really expensive. It does it a lot of times, but we can optimize it because the power term is constant for the entire tick. So we're going to pull it out of the loop. It's a spot optimization. It makes the card minorly harder to follow because you can't actually read the POW in the line, but we're going to do it because that's what we need to do to get the performance back. Okay, so there's the change. We pull the term out up above the loop, and the power line just becomes a straight multiplication. There we go. So we got about a 3 times performance improvement. We're from 1,352 particles up to 4,400 particles. Okay, we're going back into analysis mode. Where's our time going now? Well, it's spread around a little bit, but the majority of the time is going to calculating the offset for pulling the particle in. Okay. There's also a little bit of time in the where we're removing the expired particles, but it's not high enough right now to hit our radar. So what are we going to target? The distance calculation. It's around about 45% between those two lines. So again, it's expensive math a lot of times. So if we take that code and we write it out as a formula, we're calculating the offset, and then we're taking the pull radius, we're comparing it against the square root of the dot product of the offset. That's what a length calculation does. Okay, but we don't need to actually be comparing that. We can compare the squares by squaring both sides. So again, it's slightly less clear code. It doesn't. You're now dealing with a square of the length or square of the distance rather than directly dealing with the distance. But we're going to do it. So here's what it looks like. You pull the square of the radius outside of the loop because you don't want to do that all the time, and you convert it to using the squared distance. You also have to, inside the if statement, take the square root of the squared distance because we were using that inside the code. Okay, got about a 0.3 times performance improvement. That's about a third. So, yeah, gone from 4,400 particles to 5,600 particles. Cool. Next analysis. We have a time delta. Sorry, I'm having trouble reading my own slides now. What's expensive? Well, it's kind of all over the shop. Like, it's almost a little bit death by paper cutsy. But there's one thing I notice about this code, and it's all of the lines where we are accessing the pointer, the particle pointer, is where it's expensive. There's also a bunch of time here, but again, it's not high enough to be on my radar yet in the remove from particles. So what I'm going to target here is I'm going to try removing the pointer indirection because I'm frankly wondering if there's some unique pointer overhead going on here. It seems kind of surprising to me. I thought unique pointer was pretty cheap, but let's have a look. So we're just going to dereference the pointer at the top of the loop, use a reference instead. Again, it's going to be slightly less code, but slightly less clear code, but it's also a spot optimization. So here's what we do, where the new code has the dereference to a new variable called particle ref, and everywhere that we were using the indirection through the unique pointer, we're now directly referencing it through a particle ref, which is also a pointer, but effectively. So I don't expect any time back from this, really. I was wrong. 0.15 times performance improvement. So we went from, we've got almost 1,000 or around 1,000 extra particles a second by doing that. That one surprised the heck out of me. I didn't think there was enough overhead to the unique pointer to cause that, but there you go. That is why we measure. Okay, finally, we've got another analysis, and the first thing I note is that the first line where we're accessing the particle is the vast majority of the time. So the math is still expensive in there, but it's always that first line that's expensive. So I'm predicting that we've got some caching and memory access costs going on here. So we're going to turn the standard vector of particles to store particles directly so that they're in a big flat buffer rather than going through pointers and traipsing through memory. It's going to make it more expensive to move the particles. That could bite us. I don't know. If we want to make partitioning optimization in the future, this is going to potentially have consequences. And this isn't in module optimization, right? It's going to affect multiple functions through the entire code. So I'm going to whip through the code change because I think probably everyone gets the gist of what's going on here, and a lot of it's kind of uninteresting. But that top line is really the meat of the change. We're just removing the unique pointer from it and allocating a buffer directly. When we're iterating through, we're no longer having to interact through the unique pointer in the two loops that we've got. And then finally, when we're allocating the particles in the particle buffer, we're going to do it slightly differently using a reference instead of newing up the pointer and then pushing it back. Okay, that was a 3 to 4 times performance improvement, proving that memory is once again king, or memory access times are once again king. And we're up to 26,310 particles in our 10 seconds, 0.38 of a millisecond to simulate one tick. So we're past our performance target now. I've got another analysis here. You can see that it's pretty flat. It really is mostly death by paper cutsy at this point. And basically, that's what the performance improvement looks like on all of the different particle buffer sizes. So we've got in aggregate, from the first version to the last version, we've got a 38,000%, I think it was, in performance improvement. So 380 times more particles are being simulated. It's worth noting that some of the percentages looked really small when we were going through, but as it was just from the previous measurement, they really stack up because you're multiplying them all together. And that's the end of the demo. Any questions? I've even got time for questions. My goodness. Anyone? Questions?
How
So the question is basically, if you have a situation where you are effectively changing the API of whatever code you're touching so that it goes out through the entire system, how do you justify that? And it's really hard to justify. Honestly, there are plenty of optimizations that would probably be a good idea in the ideal world where you just don't do it because it's going to touch too much code. That's the reality of the situation. Again, like, if possible, you want to push decisions like that under your API boundaries so that you don't have to worry about it quite so much. But when it comes to things like unique pointers, I tend to say I would prefer people use them than not use them. I think you've just got to understand that if you're dealing with a data structure that's got 100,000 elements in it, that you might want to encapsulate that. You might want to make it an internal decision on what data type you have so that you can remove the unique pointer from that specific use case. But yeah, in the cases where it's part of your API, you're kind of shot. Yeah, so the question was, are there optimizations that were specific to fighting games that I think could be applied to other games? I mean, in reality, I think that optimization is optimization. I will say that we were very heavily task graphed. And I've seen a lot of engines out there that are, but I've seen a lot of engines that aren't as well. And that's something I would heavily recommend people invest in, like making it easier to multi-thread, having dependency chains so that you can think about the critical path. I mean, that's the type of thing that we did and that I noticed about our code base, looking at profiles of other code bases, we would just be like utilizing all of the resources for a lot of the frame. Not for all of the frame, but for a lot of the frame, we would just be saturating all of the resources. And it's quite hard to do that when you're manually pulling out small pieces of code. But I mean, it's kind of outside the bounds of this talk because it's asynchronicity. But yeah, that's one thing that I saw that I think is really important.
20 minutes remaining.
Any more questions? Sure.
For your demo thing, all particles seem to be independent of each other. Would that be a good situation where you might defer that to the GPU, which can do things massively parallel?
Absolutely. Like if you were actually writing that code in real life, yeah, you would absolutely throw it on the GPU. Sorry, I should have repeated the question. All of the particles seem to be independent, so would that be a good use case for throwing the particles up on the GPU? And the answer is absolutely. I would not, if I was writing a particle system these days for an actual production game, I would absolutely be targeting the GPU. If you can claw it from the fingers of your, the cold, dead hands of your rendering engineer. Hi, another question. Unfortunately not. Pix timing capture is probably the closest we've got, but it doesn't track dependencies between things. The tools that I've seen that are really good for that were in-house written tools, unfortunately. And when you've got them, it's amazing, and when you don't, it kind of sucks. Yeah. I'm sorry, I wish I could say different there. It's actually something that where I think software engineering needs to go, being more explicit and about what the dependencies are between the work. Right often we quite often have post hoc ergo propter hoc, which is Latin and from the West Wing, where I learnt it, that says after it, therefore because of it. So you have some code that follows another piece of code and you immediately assume that there's actually dependency between them. Or you have to very carefully go and check that there is not dependency there in order to change the code. when you get more explicit about what your dependencies are, you know that information up front. That's why I love task graphing.
We're at time.
Thank you, everyone.